Hi, this is part two of Newton's second law for rotation. I talked about the first part of the theory, basically how the angular acceleration is proportional to the net torque, directly proportional, inversely proportional to the moment of inertia. And I gave the analogy with the Newton's second law, F net equals ma. It's the same idea. All right, so I'm going to do number 43. Okay, here it says in order to get a flat uniform cylindrical satellite spinning at the correct rate, engineers fire 4 tangential rockets as shown in the figure. If the satellite, so the mass of this is 2,600 kilograms, has a radius of 3 meters. What is the required steady force of each rocket? So here we're going to say, well, the net torque is I alpha, okay? And I think here we could probably figure out the alpha first. So 30 RPMs is equal to 30 times 2 pi over 60, which is pi basically, radians per second. So if you want to find alpha, it takes, it goes from 0 to this speed in 300 seconds. So that's your alpha. The net torque is created by 4 forces at distance r away, which is 3, equals the I for a cylinder or a disc is 1/2 m r square times that alpha. Okay, and when you finish, you should get an answer of 10.21 newtons. Let's look at the next one. Number 44. Okay, so we're trying to figure out the acceleration. So here again, we're going to do the net torque equals I times alpha. Yeah, so the torque by this 3m is 3m. I'll just do m instead of mo. G times how far it is from the axis of rotation or the pivot point. This one gives us a counterclockwise torque. The other one gives us clockwise torque, so we have to subtract that. So that's going to be mg times 2L equals, well, they have two single masses, so basically the moment of inertia is going to be 3m times L square plus m times 2L square times alpha. So now if you simplify this correctly, you should get g, let me see, you get g over, what is it? G over 7L, so it's got to be A. I think that's the one. Yep, okay. Let's look at 45. If you read 45 carefully, it says that for that little period of time, the object is not moving, so the net force on it should be 0. Okay, now we're going to try to find the linear acceleration caused by the person's hand. So here I think we can say for 46, I'll just do it up here. So torque equals I alpha. Now the torque is generated by T, which when the object is at that rest is equal to mg. So it's mg times the radius of that hoop, okay, equals, it's a cylinder, 1/2 m r square, and A is r alpha, so alpha is A over r. So I think all the r's are gone, so you're left with one r here and one r here, and this m is gone, so A is equal to 2g. For 47, well, counterclockwise is positive, which means the object was moving counterclockwise. and then this force came in. So it had a positive linear angular acceleration, and when these forces came in, this one created a bigger torque. So it starts to slow down, right? And it has to go in the clockwise direction. So the answer should be C. Okay, 48. A wheel with rotational inertia I is mounted on a fixed frictionless axle. The angular speed omega of the wheel is increased from 0 to omega f in a time interval t. What is the average net torque? So torque is I times alpha, which is I omega final minus omega initial over time. So it should be that, which is, according to my notes, it's what is it? It's D. Okay. To find the power, we're going to do the analogy with the translational stuff when we did power. So power, if you remember, we said it was force times the average velocity. Well, the same thing here. We're going to say power, but instead of force, we're going to replace it with torque because of that analogy. And here, it's going to be the average angular speed. So the torque, I think we found it to be I omega f over t. And the average omega is just going to be omega initial, which is 0, plus omega final over 2. And if you do it right here, you should get I omega square over 2t, so it should be B. Number 50, I did in the first video, so I'm going to go right to 51. So now here you have a solid disk, okay, with that radius, and you have a torque of that much, right? What's the angular acceleration? So this should be easy. Okay, so the torque is 6.4. Since this is a disk, it's 1/2 m r square, okay, times alpha. And alpha is equal, I don't have it here, but you can look at your answer key. Okay. A Ferris wheel, it's a 2,000 kilogram Ferris wheel, accelerates from rest to an angular speed of 2 radian per second in 12 seconds. So right away, I think we can say that the alpha is 2 over 12, which is 1/6 radian per second per second. So approximating the wheel as a solid disk, that's actually between a solid disk and a hoop because it's got those spokes in the middle. What's the net torque? So torque equals I, right? So torque equals I alpha. I is 1/2. We're going to do the I for a disk. 1/2 m r square times 1/6. And again, you could probably do this mentally. So let's see. So I think I can write this 30 as 30 times 30, right? And then I can get rid of this half, make that 1,000. Okay, and 30 divided by 6 is 5. So we get 150 here. So, and just add 3 zeros. Okay, meters times newtons. Okay, and that should do it. Thank you.